All right, so recall that with vertical curves, we're looking at a curve either of a crest type or a sag type. There's of each of those, there are two subdivisions. So we have a crest that can go from a positive to a negative, a crest that can go from positive to positive or negative to negative, as you can see here on the right-hand side of the screen, these type 2 curves. And then similarly for the sag curves, right, our basic type is one that goes from negative to positive, but we can also, under the type 4 curve shown here, go negative to negative or positive to negative. And unlike the horizontal curves, which we were using a constant radius for, these vertical curves are modeled using a parabolic function, but we use some similar terms to those that we use for the horizontal curves. So we had point of curve, point of intersection, point of tangent, length of curve, so on and so forth. For the horizontal curves, here we in effect have same thing. We just throw in a V, PVC, PVI, PVT, to denote that we're talking about vertical curves specifically. And we also have to define what the initial and final grades are. So that's what the G is being shown here in these images. And we also use A, which is the overall change in grade. And then you might remember too that we used a variable K, where K just shows the relationship between L and A, so the overall length of our curve, and how much grade is changing over that length of curve. So you guys should all be fairly familiar with the parabolic function at this point. So ax squared plus bx plus c. So in this case, we are using y to represent our roadway elevation. We are using x to represent the distance that we've moved away from the PVC. And then we're using c to represent the elevation change that's occurred, or sorry, the elevation of the PVC, because y is the roadway elevation. And so usually we're designing for equal length tangents, again, meaning that the distance between the PVI and the PVC is equal to that of from the PVI to the PVT. So half the curve is happening before the PVI, and then half of the curve is then happening after. And in this type 1 curve here, you can see that quite well. Right, we got L over 2 before the curve, and then also here would be equal, same thing, L over 2. And the same holds for the type 3 and type 4 curves. So you can see this down here for the type 4, right? At this point here is our PVI, and half the curve is occurring between the PVC and the PVI, and then half the curve is occurring between the PVI and the PVT. So in general, like I said, we're 99% of the time we're going to be designing equal length tangent curves. So moving on from that, if we take that parabolic function, so I'll just rewrite it here for reference. Oof, pen's going crazy. Ax squared plus bx plus c. And if we were to take the first derivative of that parabolic function, we'd end up with 2ax plus b, right? So the c term drops out. So we're taking the derivative with respect to x. And that gives us this 2ax plus b equation. And when we take the derivative of a curve, that function we're left with represents the slope, right? So this function here, dy dx, is going to tell us what the slope is at any point on the curve when we specify a value of x. And remember that x is what we're saying is the distance that we've moved away from the PVC. So we know that when x equals 0, we're located at the PVC, right? So here's my curve, here's my PVC, here's my PVT. I'm going to very, crudely draw, a y and an x scale on here, assuming this is our origin, right? So that's why I was saying just crudely drawing y and x. But if I were to have it intersect here, right? So here's my x-axis and here's my y-axis. When x is 0, I'm sitting on the PVC. I haven't moved anywhere away from the PVC. So I know at that point, right, if I put a 0 into this equation here, so I've got 2 times A times 0 plus B. This term's going to drop out, and I'm left with B. And B is giving me, or dy dx is equal to B. And because it's giving me slope, right, what's the slope at the PVC? Well, it's just going to be the initial grade of the curve, right? So in this case, we can use that in our favor, where we know that B in the parabolic function here is just going to be the initial grade of our curve, and so that's given in feet per feet, right? It's unitless in this case, but represents the change in slope right at the or the slope of the road at the PVC. So if we take the second derivative, and so that's where I slightly misspoke just a second ago. If we take that second derivative, that's what's giving us that rate of change of slope. So recall previously we had dy dx. Oof, pen is not having, come on. Pen's having a hard time. So dy dx was 2ax plus b, right? So if I take the derivative with respect to x of that, the b is going to disappear and our x is going to disappear, and we're left with 2a. So that's our rate of change of slope. But we also know that the average rate of change of slope, just by observation, can be written as the overall change in grade over the length of the curve. And so that's what I've got down here in this equation there. So if I take my final grade, so grade 2, which would be the grade at the point of vertical tangent, and I subtract off my initial grade, divide by the overall length of curve, then that would give me what the overall in total average rate of change would be. So if I take that and were to plug this back in up here, right? So G2 minus G1 over L is equal to 2A. I can rearrange and solve for A in this equation, which would give me G2 minus G1 over 2L. So having derived those key elements, we can determine a number of key points for the curve, again, assuming that it's an equal tangent parabola. Also note that the offsets that we're computing are vertical distances from the initial tangent to the curve. So when I say initial tangent, I'm talking about this point here at the point of vertical curve. So when I specify a value of x, what I'm getting out of the equation is this offset here, right? The difference between this tangent line and my curve. Wow, come on. Between the tangent line and the curve, right? So here and here, and I'm getting these values, right? So if I were to specify this value of x here, I would get the offset between that tangent line and the curve. So I need to go back one here. We're going to use A and L as we defined previously. So A being the algebraic difference in the curve, and L being the overall length of our curve. So if we want to know the offset at the midpoint of the curve, which would just be L over 2, I could put that into this equation here. So I've got I've got 200 times x squared. So my x in this case is L over 2. And if I put L over 2 in for x here, I'm going to end up with an L squared over 4, right? So one of those L's will drop out, and then I've got a 200 times 4 in the denominator, which leaves me with this equation down here, right? So this AL over 800 is just A over 200L times L over 2 squared, right? So I would end up with A times L squared over 200 times L times 4. So L drops out, and I'm left with A times L over 200 times 4. So that's the offset at the curve midpoint. And then similarly, right, if I want to know the offset at the end of the curve, which would be here at the PVT, then for X, I would just put in, no, it's not like just a value of L for X. And that would give me Y equals A times L squared over 200L. And so in that case, my L's drop out, and I'm just left with AL over 200. And then I just, recall we talked about whether we're talking about feet, we're talking about stationing. So if I wanted to know at the midpoint of the curve what the offset was, and I'm using stations, each station on a roadway is 100 feet. So I'm just putting in a factor of 100 there to account for stations. So just note that this equation here is applying to the midpoint of the curve. And then this is just a good point to note that that overall rate of change is going to be constant over the whole curve. So if we know what the initial grade is, what the final grade is, and what our overall curve length is, and that's what's being denoted here. So L is the overall length of our curve, A is the overall change in grade, that K here is going to represent our rate of curvature, which is in effect the distance that we need to travel X in that equation in order to achieve a 1% change in grade. But then we can choose any, so this portion of the equation here on the left-hand side of our slide just notes that if we choose any 2 points on the curve, M and N, so that can be say here M and here N, provided that we know what the distance is to M and what the distance is to N. Oops, not a 2, an N. And what the grades are there, or we can back calculate what the grades are there, knowing that A over L or L over A has to remain the same. Recall that our 2 general goals in vertical curve design, one, we have to provide adequate stopping sight distance for safety. The other is that we want to minimize the curve length, which often is going to reduce the cost, because oftentimes we're having to construct these curves unless the topography happens to be working in our favor. So in this image on the top right, you can see the sight distance issues, right? So if I were to draw, a line of sight coming from 3.5 feet up, it's going to hit about here, right at the horizon line. And that if an object were sitting on the back side of that curve, it's going to be very difficult or impossible for us to see it. So we need to be sure that we're allowing a full stopping sight distance prior to those obstacles on the backside. So you should be familiar with the stopping sight distance equation, which includes the distance traveled during perception reaction and the distance traveled during braking. Recall that we can use our reference tables here to pull out stopping sight distance, but that these are all for a grade of 0. So we always want to take whatever the limiting factor is on our grade and compute that out just for the purpose of being conservative. So integrating that into our equations for vertical curves, we have the first case where our stopping sight distance is less than L. So that is here that the stopping sight distance is happening entirely within the point of vertical curve and point of vertical tangent. So all of the stopping sight distance is contained within the confines of the curve. And we're also, recall, assuming that the height of the driver's eye is 3.5 feet. The height of our obstacle, which would be the height of a tail light, is 2 feet, which allows us to reduce that equation, if we're using the AASHTO standards, down to this equation in blue here on the slide. So we have A, which is the difference in grades, stopping sight distance squared over 2158. We also have the case where stopping sight distance would be longer, than the length of curve. So here, that the beginning and ending point that represent that full stopping sight distance extends beyond the point of vertical curve and the point of vertical tangent. So there's a portion of the full stopping sight distance that happens on the initial tangent, or a portion that happens on the second tangent of the curve after the point of vertical tangent. Now, mind you, here on this diagram, I've drawn it so that some of the stopping sight distance is on tangent 1 and some of the stopping sight distance is on tangent 2. But you could have a case, right, if the driver were located at this point here, that the full stopping sight distance, would occur something like this. So it would just extend out that portion of the stopping sight distance that occurs on the second tangent. Again, if we assume the AASHTO standards for height of driver's eye and tail light height, we can minimize that equation and reduce it down to the equation here in blue. So 2 times the stopping sight distance minus 2158 over the change in grades. And that's for crest curves specifically. For the sag curves, recall that we are concerning ourselves with, in effect, nighttime driving for the sight distance issues. So we have to take into consideration the height of the headlight and the angle at which the headlights shine. And doing so reduces us to these 2 equations here. So we have the case where the stopping sight distance is greater than the length of curve, and the case where the stopping sight distance is less than the length of curve. And then we also have these secondary minimum length requirements to compute for both comfort and appearance. So one thing to note here is that, and you might remember this piece of advice from intro, that because we have 2 conditions for initial conditions for crest and sag, right? So we have S greater than L and S less than L, S greater than L and S less than L. And basically, like 4 equations that I said that the one to start with, because it just needs to meet one of these 2 conditions, right? separate these out. So if we're looking at a crest curve, like it's either going to meet one or two, right? And then for a sag, it's either going to meet one or two. It can't be both simultaneously. So it's always better or quicker to check the case where the stopping sight distance is less than L. It's more often than not that case. So we would check this first. If it meets that criteria, then we're good. If not, we'd just go back and use equation 1 and compute that out. So like I said, if it doesn't meet one of them, it's going to meet the other. So then for the sag curves, we just also have to check the comfort and appearance, but we don't have to check comfort and appearance for crest curves. The other thing that we have to consider is the case where we're going underneath an obstacle. So recall that the clearance height of that obstacle, depending on how high it is, can impede the line of sight. So beyond just needing enough distance for a vehicle to pass underneath that the overpass or obstacle, that we also don't want to impede that line of sight. So we need to check that as well. That's only specific to sag curves and not to crest curves. And you'll see the two equations here. One is for when stopping sight distance is greater than the length of curve, and then one for where the stopping sight distance is less than the length of curve. All of the elements here remain the same as the previous equations. So we just have our stopping sight distance, we have our driver's eye height and the obstacle height, our algebraic difference in grades. And then the new piece to the equation is what that clearance height is. Remember that we do also have minimum height requirements. So we might go through these equations here, compute out possibly that the minimum length of curve would lead us to a value of C being something like 8 feet. But 8 feet is not really high enough to allow any average vehicle to pass under it unless you got a really small passenger car, but most large tractor trailer trucks are much taller than that. So we do have some guidance from AASHTO on the minimum vertical clearance heights. So for freeways, anywhere from 14 to 16 feet. If we're on a arterial, also 14 to 16 feet. If we're on local roads or collector roads, at least 14 feet. So we could start here and use, C is 14, and then compute out what our length of curve would need to be in order to maintain that clearance height. Also note that the K values are based on grades being equal to 0. So specific grades need to be accounted for when we're looking at downgrades where more stopping sight distance would need to be required, or upgrades where less stopping sight distance would is required. And like I said, that last piece of advice there is if you're not sure which equation to use for sags and crest, always assume that stopping sight distance is less than L first, and then go from there. So let's pull up the example sheet. So I've got the same one written here on the slides, but I'm gonna switch over to the PDF. So the problem we're looking at is designing a sag vertical curve, and we're joining a negative 5% grade with a positive 2% grade, assuming the design speed is 40 miles an hour, and we want to determine the minimum length of curve that's going to satisfy all the criteria. So we're going to use the standard deceleration rate, perception reaction time, and the AASHTO assumptions for driver's eye height and obstacle height. So does everyone have their example sheet up and handy and ready to go?
Yep.
Yep.
Cool. So the first thing we want to do here is determine what our stopping sight distance is going to be. So remember that stopping sight distance is 1.47 UT plus U squared over 30 A over G plus G. I'm gonna make my pen a little thicker here. So we've got 1.47. We said design speed is 40 miles an hour. Perception reaction time, 2.5 seconds. And to that, we'll add 40 squared over 30, 0.348 for A over G, right? Remember that A over G is 11.2 over 32.2. So 11.2 is our standard deceleration rate. 32.2 is acceleration of gravity. And then to that, we will add a negative 0.05, right? So in this case, a negative 5% grade is my limiting, the limiting grade here. And that works out to be 324.78 feet for my stopping sight distance. So the next step is to figure out whether we have the case where S is greater than L or that S is less than L. And like I said, we're going to try stopping sight distance less than L. If we were smart, I'll do the opposite in this case just to illustrate how to deal with it if we incorrectly pick the wrong one, or if we pick the wrong one first. So I'll write out here, so assuming S greater than L, my minimum length of curve would be 2 times the stopping sight distance minus 400 plus 3.5 times the stopping sight distance over A, which gives me 2 times 324.78 minus 400 plus 3.5 times 324.78. And that is over the algebraic difference between -5 and +2, which would be 7. So L min is 430.3 feet. So I need to check that S is greater than L. So is 324.78 greater than 430.3? Obviously not. So, right, doesn't meet the criteria. So I need to go back and instead assume that S is less than L. So for S less than L, our L min equation is going to be A times stopping sight distance squared over 400 plus 3.5 times stopping sight distance. So we already said that A is 7. So I've got 7 times 324.78 squared over 400 plus 3.5 times 324.78, which gives me 4 80.48 feet. So, you know, just to be sure, right? I mean, you can all see where I'm going with this. Check that S is less than L. So is 324.78 less than 480? Well, of course it is. So we're good to go there. Again, just to illustrate what's going on there, we've got a curve, we've got a point of vertical curve and a point of vertical tangent, and we're just saying that the length of the stopping sight distance is happening within the confines of the point of vertical curve and point of vertical tangent. Also note here that just because what I'm doing here is drawing, I'm marking this point as the origin of my stopping sight distance, and here's the termination of my stopping sight distance. And even though I'm drawing just a completely horizontal line between these two to denote that's where the stopping sight distance begins and ends, is that the stopping sight distance, even though it is in part taking into account how far I'm able to see ahead on the road, that it must consider in actuality how far it's going to take the vehicle to stop, right? So if I'm a vehicle traveling along this road, that distance is actually going to be along the curve. And then the same goes for the distance between the point of vertical curve and the point of vertical tangent, right? Is that I'm talking about, or sorry, the length of curve, right? Is I'm talking about moving along the curve itself and not the straight line distance between the two, because one is a chord. Remember, we talked about that previously in the horizontal alignment lectures, the difference between chord and arc. So our stopping sight distance is actually an arc length, as is our length of curve. Okay, so that said, we have 480.48 as the distance that's going to satisfy our L min for sight distance. So I'll just put a highlight on that. So we still, because this is a sag curve, I need to check our comfort criteria and our appearance criteria. So the first for comfort, we have L min is equal to A times U squared over 46.5. So 7 times 40 miles an hour squared over 46.5, and that equals 240.86 feet. And then we need to check the minimum length for the appearance criteria. So L min is just going to be 100 times A, so 100 times 7, which gives us 700 feet. So based on those computations, right, it's not just sufficient to stop there, because we can't have three curves, all of three different lengths that exist in the same location. We have to pick one of those, right? And so we want to pick the most limiting of those. The most limiting is going to be the value that is the largest. So we would say, therefore, L min that meets all criteria is 700 feet. Makes sense? Good refresher. Sounds familiar?
Yeah, I remember doing
All right, so what I want to do next, based on that, the next problem here is an overpass that's being built uh, over a PVI, so directly over the PVI of an existing equal tangent sag curve. A little bit faster, so design speed of 70. You've got initial and final grade, so it's still a sag. And I want to know what the minimum necessary clearance height needs to be over the overpass. And in addition to that, what the corresponding elevation is of the bottom of the overpass at its midpoint over the PVI. So just to mix things up, what I'm going to do here is send you guys into breakout rooms like I did previously. So we've got 7 folks today. So there'll be one group of 3 and 2 groups of 2. I'm just going to mix it up. My memory is not the best, so maybe some of them will be the same. But I'm gonna, let's see here. I'll start off with 2. So I'm gonna go McKenna and Russell. You're in one group. And Ryan Taylor, you're in another group. And then Alex, Connor, Steven, you'll be in the last group. And I'll just bounce back and forth between each of the groups. You guys should have screen sharing capabilities. So if somebody wants to share and show me where they're at and walk me through it, that's fine. I can also, we can also just talk through it as well. So what I want you to do is, again, as the problem statement indicates, I want to know basically what the, based on the computation, what the minimum length of curve needs to be, and then what the minimum clearance height would then need to be. And beyond that is also what would the, or what is the elevation at that point, at the midpoint over the PVI. So go ahead. When I click this button, it's going to give you an invite to join your breakout room. So just go ahead and accept that, and then I'll just bounce back and forth between each of the rooms. Ready, break. All right, Russell, McKenna, what? So just to get you started, what's the first thing you need to do?
First thing we'll have to do is go ahead and determine the stopping site distance.
Bingo. Yeah. So get your stopping site distance, and then after you've got that, start working through computing what your L min will need to be based on those curve characteristics.
Okay.
So I'll let you get started on that, and I'm gonna bounce off to another room. Sweet. Taylor, Ryan, how are we?
Pretty good. We're taking a look at it right now.
Yeah, so just to get you started, first thing, right, that you need to do, compute out the stopping site distance, right? So design speed 70, and then your most negative of the grades, right? So get that stopping site distance, and then once you got that, you start working through what the minimum length of curve is going to be based on that stopping site distance, comfort, and appearance criteria.
Okay, so the same thing we did in the first problem for the first step.
Yeah, so get yourself to the point where you've figured out L min, and then we'll go from there.
Okay. Thank you.
Yep.
See you here shortly. All right, gentlemen, how we doing?
Pretty good.
Pretty good.
So if you haven't already, right, place to start is get your stopping sight distance. So 70 miles an hour and the most negative of the grades for the curve. So we've got -5, right? So use those two values. Everything else should be the same. And then once you got that stopping sight distance, then go ahead and work through those L-min equations. So for stopping sight distance, comfort and appearance, and find which of those is the most limiting, meaning which one's the largest, and then we'll move on from there. So get yourselves to a point where you've got that SSD and those L-mins, and I'll check back in on you shortly.
Thank you.
Don't feel like you need to be quiet and work on these alone. That you're here to work with each other, to make use of it while you can. Okay, so what I'm going to do here is show what would have happened had we used the K values. So we said U. Ooh. U design was 70. Man, going back and forth between drawboard and the whiteboard is a little challenging, but U design was 70. And using the tables, the K tables from the green book in that vertical curve chapter, we're told that the K value is 181. And again, that K is coming from L over A, right? It's a constant rate of change in the slope. And that's also based on, and we know that for our two grades that A was 8, right? We're connecting a -5 and a +3. So if we take L times KA, that's going to be equal to 8 times 181. And that gives us 1448 for our length of curve. For a design speed of 70, right, we already said that our stopping sight distance, we'd computed that previously as 802 feet. And so we can come into our minimum length of curve for our clearance height as A times SSD squared over 800 times C minus 5. And I can rearrange that as you guys just did. So I've got C equals A times SSD squared over 800 L plus 5. And that works out to be C equaling 8 times 802 squared over 800 times 1448, and then all that plus 5. And that gives me a value of 9.4 feet. So basically the same value that you guys had gotten previously. Obviously that's not enough, so we'd have to go with a minimum C of either the 14 feet, or I think Russell and McKenna chose 16 feet, 16 and a half feet to be conservative. Again, that's just fine. The only other place where this can possibly be problematic is in the next piece of the equation. So we said we were computing the middle offset, so A times L over 800. And in this case, that's going to be 8 times 1448 over 800. And that's going to give me 14.48 feet. All right, so that's a little different than the 16 feet that you all had just computed previously. And what is the reason for that? So if I were to carry that through the problem that we just worked through, right, I'd say that the difference between the elevation at PVI and the overpass would then be 14 feet plus 14.48 feet, which gives me 28.48 feet, which is different than the 30 feet you had computed. So why is there a difference of about 1.5 feet there compared to how we had just worked it out?
When we worked out our actual stopping site distance without using the K value, we had about 200 or so more feet on there. So the overall smaller bit being carried through just means that like our estimate is a bit shy.
Yeah, so Russell, this number here specifically, right, that 1448, because those K values, remember we said those K values assume an initial grade of 0, right?
Yeah, instead of the plus 3%.
Right. So it's always better, and so this is just to reiterate, it's always better if we compute those things directly. K can work in our favor in a number of cases, but it's always better to be conservative. And so to the best of our ability, we want to be able to do that, or just be cognizant of that. Okay, so that brings us to time. So we'll end there for today. Like I said, I'm gonna do for you guys, I'll do problem 3. I'll work it out and record it and post it for you guys. So consider it just being a piece of your homework to watch. But we will have a homework due for next week on this. So check the drive here later today. I'll be putting it up here in the next 30 to 40 or so. So it'll be due next week. I sent back homework 1s last night. I'm almost done homework 2s. So keep an eye out on your inbox for graded homework 2s as well. And then I saw a flood of your homework 3s come in this morning. So if you forgot to do that, make sure you do that here as soon as possible. Any questions?
Nope, should be good. Thank you, Dr. Bells.
Thanks, Russell. Anyone else? Everyone's good? Feeling great?
All good. Thank you.
You're welcome, Ryan.